This conservation of energy example involves all three types of mechanical energy that we've looked at. So we have kinetic energy, we have gravitational potential, and we also have spring potential energy. So the real question for this one is, how far is the spring going to compress? So we have this ball or this object, whatever it is, that's moving to the right at 40 meters per second. You know the mass of the ball, and it's going to go up this hill. We know the height of the hill. It's going to compress this spring. So we want to figure out how much is that spring going to compress when the ball comes to a stop, because it's going to hit the spring, push the spring in, it's going to slow down, it's going to stop. The question is, how far is it going to be compressed once it's stopped? So I'm going to just take a look at the different points I have. In fact, I really only have 2 points here. I have the initial point, and then I have this point here at the end that I'm worried about. So if I label my energies, so at the initial point, we have kinetic energy, we have gravitational potential, spring potential, and then the total energy at that point. And then at the second point, over here when it compresses the spring, we have kinetic energy, we have gravitational potential, we have spring potential, and then we have our sum of energies. So I'm just going to label all of them. If some are 0, I'll put 0 in there. If it's not 0, then we'll find the actual value there. So initially, I have kinetic energy because I know it's moving here. So the kinetic energy is 1/2 times the mass, which is 5 kilograms, times the velocity, which is 40 meters per second squared. So I can figure that out. So 0.5 times 5 times 40 squared, that gives me 4,000 joules of kinetic energy. I don't have any gravitational potential energy because it's at my lowest spot here. So relative to the lowest spot, it's there, so it has no height. So it has 0 joules. It's not compressing the spring. It's not even touching the spring right here. So I have no spring potential energy. That means that the sum of my energies is 4,000 plus 0 plus 0. So it's just 4,000 joules. Now the reason that's helpful is because in the second point, we also have a total energy of 4,000 joules because of the law of conservation of energy. So at this point here, I basically just have to figure out some of the rest. And for the rest of it, since the spring is going to come to a stop, I know that, or the ball is going to come to a stop, and the spring is going to come to a stop. There's no joules of kinetic energy once that spring is compressed, the farthest it can compress. For potential energy, for gravitational potential, I know it's the mass, so 5 kilograms, times the acceleration due to gravity, so 9.8 meters per second squared, times the height, which at that point is 7.8 meters. So I can figure that out. So 5 times 9.8 times 7.8. That gives me 382.2 joules. Then for my spring potential, I know it's going to be 1/2 times K, which is 14 newtons per meter, times x squared. I don't know what x is. That's really what we're trying to find here. So if I really wanted to figure out then what x is, I know that the sum of my energies is going to equal the total energy. So that means 0 joules, I'll write 0 here for now, plus the gravitational potential is 382.2 joules, plus 1/2 times 14, so that's 7x squared equals 4,000 joules, and that's 7 newtons per meter times x squared. So then if I just simplify, I can subtract 0, which I really don't have to worry about, subtract 382.2 joules from both sides. So 4,000 minus 382.2 joules. So I have 7 newton per meter x squared equals 3,617.8 joules. If I divide both sides by 7, so by 7 newtons per meter, I get 3,617.8 divided by 7, which is going to be 516.829. It ends up being meters squared. The reason why is because joules is a newton meter. If you remember some of the simplifications we did earlier, it ends up being a newton meter. If you take that divided by newtons divided by meter, the newtons cancel out, so we have meters over 1 over meters, which is the same as meters squared. So that's where that unit meter squared comes from. So all I have to do then is take the square root of both sides, and that gives me my displacement of the spring. So the square root of this is 22.734 meters. That's one pretty hefty spring to be able to be compressed, 22.734 meters. But that's what we get when this ball is traveling at a pretty high rate of speed at the beginning, and it's a pretty massive ball already to begin with. So that's why we have a pretty good compression of the spring, but that's going to be our answer.